So in this lecture, we are going to discuss arrangement of flow paths in heat exchanger. Then we will apply LMTD method for parallel flow and counter flow heat exchanger. So let's start with the first topic, which is arrangement of flow paths in heat exchanger. In heat exchanger, there are some flow patterns like counter flow heat exchanger, parallel flow heat exchanger. We know in a parallel flow heat exchanger, the direction of a fluid flowing of hot fluid and cold fluid are same. As you can see in this figure, the flow direction of fluid 1 and fluid 2 are from left to right. So this is the first flow patterns which is in parallel flow heat exchanger, the two fluids flowing in the same direction. Second flow pattern is for the counter flow heat exchanger, in which the fluid flow direction of hot fluid and cold fluid are opposite to each other. As you can see in this figure, the fluid 1 is flowing from right to left and the fluid 2 is flowing from the left to right. So two fluids flowing parallel to each other but in an opposite direction. The third one is the cross flow. As you can see in this figure, two fluids crossing each other. In this figure, the fluid 2 is flowing from the pipe in this direction. The fluid 1 is flowing around the surface of the pipe in this direction. So it is a right angle to each other. So this is a cross flow pattern. Also in this figure you can see the fluid 2 which is flowing from the pipe in this direction. The fluid 1 is going to flow around the surface of the pipe of the fluid 2. So this is again cross flow pattern. The next one is a mixed flow pattern, which is generally seen in the shell and tube type heat exchanger. In shell and tube type heat exchanger, one fluid is flow from the shell, as you can see in this figure, and the another fluid is going to flow from the pipe. So the one fluid is going to flow around the surface of the pipe in which the second fluid is flowing. So this is a mixed flow. This is the second example from the mixed flow. Both fluids are flowing simultaneously in parallel flow as well as in a counter flow. So for one pass it may be in parallel, for another pass it may be in a counter flow direction. The next one is the multi-pass cross flow. When there is a number of pass used in a shell and tube type heat exchanger, then the flow pattern is known as the multi-pass cross flow. So these are the flow patterns which are used generally in a heat exchanger. Now we are going to discuss some basic equation which are going to used in design of any heat exchanger. So we know that the temperature variation, or we can say that the temperature difference between the two fluids in a heat exchanger mainly depends on the flow path arrangement. For a counter flow heat exchanger, the temperature difference between the hot fluid and cold fluid at different location are different. For parallel flow heat exchanger, we know that at the entry point in a parallel flow heat exchanger, the temperature difference is going to be maximum, because the hot fluid and cold fluid are going to enter in the heat exchanger from the same location. So at the entry point, the temperature difference between hot fluid and cold fluid are going to be maximum in parallel flow heat exchanger. The temperature difference at the exit point of the parallel flow heat exchanger is going to be very less. In a counter flow heat exchanger, the hot fluid is entered from, suppose from the left side. So in a counter flow heat exchanger, the cold fluid will enter from the right side. So the temperature difference at the left side, suppose, is TH1 minus TC2, and from the right side it is going to be TH2 minus TC1. So the temperature difference at the different location are going to be different according to the flow patterns, according to the type of heat exchanger. So which is depends on the flow path arrangement. So for the design, first step is to denote or draw the x and y axis, and we need to plot x axis for the surface area and the temperature at the y axis. Let's understand this by example. Suppose we have counter flow heat exchanger. So we know that in a counter flow heat exchanger, suppose hot fluid is going to be enter from left side and going to be exit at the right hand side. So the temperature at the inlet is going to be TH1. The temperature at the outlet for the hot fluid is going to be TH2. As you can see in this figure, this is our x axis for the surface area, this is our y axis for the temperature. So the inlet temperature of the hot fluid is going to be the maximum temperature among the 4 temperature of the fluid. So TH1, the maximum temperature, as you can see, this is the TH1, entry point temperature of the hot fluid. TH2, exit temperature of the hot fluid at the right side. We know the hot fluid will going to be lose heat to the cold fluid, so the temperature is going to be decreased from TH1 to TH2. So here from the graph we can see that temperature decrease from the TH1 to TH2. The cold fluid is going to be enter from the location, from the right side, from where the hot fluid is going to be exit. So this is our entry point of the cold fluid at temperature TC1, and the exit temperature of the cold fluid is going to be TC2 from the location, from the part from where the hot fluid is going to be enter. So TC2 will be just below the TH1. So the temperature difference at the left side is going to be TH1 minus TC2, which is delta T1. In our heat transfer subject, we have denoted by theta 1. Here we use delta T1. At right hand side, the temperature difference between two fluid is going to be TH2 and TC1. TH2 minus TC1, which is denoted by delta T2. Done. The second one is parallel flow heat exchanger. We know in a parallel flow heat exchanger, the hot fluid and cold fluid are going to be enter from the same side. Suppose from the left side. So this is the entry temperature of the hot fluid, which is TH1. This is entry temperature of the cold fluid, which is TC1. So the temperature difference at the entry point is going to be delta T1, TH1 minus TC1. Similarly, the temperature of the hot fluid is going to be decreased in the heat exchanger. Whatever heat is going to be reduced is going to be added in the cold fluid. So the temperature of the cold fluid is going to be increased from TC1 to TC2. So from graph you can see that the temperature of hot fluid is decreased. The temperature of cold fluid from left to right is increased. So at the exit point, the temperature difference between two fluid is going to be TH2 minus TC2, which is denoted by delta T2. This is for the parallel flow heat exchanger. Now, same as well as there are two another we have classified heat exchanger based on the change of phase. So according to change of phase, there are two parts, evaporator and condenser. In evaporator, we know that the temperature of the cold fluid remains same, because whatever heat released from the hot fluid is and received from the cold fluid is the latent heat for the cold fluid. So here the phase change of the cold fluid takes place. So the temperature of hot fluid is decreased, the temperature of cold fluid is increased. But whatever heat is supplied from the hot fluid is the latent heat for the cold fluid for the phase change. So in evaporator, there is a phase change of cold fluid so that the temperature of the cold fluid remains the same, but there is a change of phase of the cold fluid. Similarly, in condenser, we have explained this evaporator and condenser phenomena in our previous lecture by taking example of refrigeration. In a refrigerator, from the compressor, the compressed high pressure and high temperature refrigerant in a vapor form enters to the condenser, where it releases the heat to the environment. So environment is our cold fluid, suppose, and our hot fluid is our refrigerant, which is in a vapor form. So in condenser, that refrigerant release the heat to the environment and convert into the liquid form. So whatever heat is released by the refrigerant in the environment is the latent heat for the refrigerant. So the temperature will remain same, TH1 entry point and TH1 at exit point. But whatever heat is loosened by the hot refrigerant is the latent heat. So the phase change takes place. That refrigerant after exit from the condenser is going in expansion valve, where the pressure drop and again temperature drop happens, and that liquid refrigerant enters into the evaporator. So now the liquid refrigerant whose temperature is low is our cold fluid. That liquid refrigerant at evaporator space takes heat from the surrounding and use that heat to convert itself from the liquid refrigerant to the again vapor refrigerant. So in evaporator, refrigerant takes heat from the environment. That heat is known as the latent heat for the refrigerant and use that heat to convert itself from the liquid to vapor refrigerant. In condenser, that high temperature vapor refrigerant loosen heat to the environment, gives its latent heat to the environment and condensed and convert from the vapor refrigerant to the liquid refrigerant. So in evaporator the temperature of cold fluid remains same, in condenser the temperature of the hot fluid remains same. Okay. Now from the first law of thermodynamics for open system, because this is a, suppose we have this kind of arrangement, this is counter flow type arrangement. As you can see, the direction of flow of the both fluid are opposite to each other. So this is the TC1 and TC2. So cold fluid is flowing from left to right. This is our TH1 and TH2. The hot fluid is flowing from right to left. This is counter flow pattern. So for open system, we know first law of thermodynamics for open system, under steady state, steady flow condition with negligible potential and kinetic energy changes, the change of enthalpy for one of the fluid can be written as, this is the change of enthalpy. Suppose we have this elementary area dA. So for this elementary area dA, the change of enthalpy, we can use this equation which we have studied in thermodynamics, that del Q is equal to mdI. Here in this equation, this m is the mass flow rate of the fluid, I is the specific enthalpy, and del Q is the heat transfer rate. So if we integrate this equation, we will get Q, because this is our elementary area. So for elementary area dQ, so for total heat exchanger we have to integrate this equation. So after integration, the total heat transfer rate for the fluid is going to be Q is equal to m dot mass flow rate, and for dI it's I2 minus I1, enthalpy at the outlet minus enthalpy, specific enthalpy at the inlet. So it is going to be I2 minus I1. So I1 and I2 represent the inlet and outlet enthalpies of the fluid stream. Now we know that for the hot fluid we can denote suffix by H, for cold fluid we will denote by C. So this equation for the hot fluid can be written as Q is equal to mH IH1 minus IH2, enthalpy of the hot fluid at the entry point, enthalpy of the hot fluid at the exit point. Similarly, IC2 minus IC1, enthalpy, specific enthalpy of the cold fluid at the exit point, and specific enthalpy of the cold fluid at entry point. We know the value of IH1 is higher than is going to be higher than IH2 at the, and IC2, value of IC2 is going to be higher than the IC1. So that IC2 minus IC1, here IH1 minus IH2. Now if the fluid do not undergo phase change, so we can write dI is equal to Cp dt. Cp is a specific heat and dt is a temperature difference. So instead of enthalpy, we can replace this by Cp dt. So instead of this IH1 minus IH2, we can write Cp dt. So here m dot as it is, Cp specific heat for the hot fluid. So mHCpH, we can write mCp in bracket suffix H for the hot fluid. TH1 minus TH2, temperature at the inlet and temperature at the outlet. Similarly for cold fluid, mCp TC2 minus TC1. In our heat transfer subject, we directly write this equation for the hot fluid and cold fluid. So from the first law, this equation can be derived like this. Now we know we have derived this equation in our analysis of heat exchanger topic in our previous lectures, that the temperature difference between hot fluid and cold fluid varies with the position in the heat exchanger. So we know that general standard equation to find out heat transfer rate is Q is equal to, for conduction K dt by dx, for convection HA delta T. So there is one constant, either K or H, but in heat exchanger there is a conduction as well as convection. So we have to use overall heat transfer coefficient, which is U, the area from which the heat transfer takes place. So area is capital A, and then we have to write the temperature difference. But we know that the temperature difference between the hot fluid and cold fluid is going to be changed according to the location throughout the heat exchanger. So we require the mean temperature difference, which can be denoted by delta Tm. In our heat transfer subject, we have denoted by theta m, which is logarithmic mean temperature difference. So which is the function of Th1, Th2, Tc1 and Tc2.